Hello, this is Team 24's final presentation where we'll talk about our analysis and redesign of a coffee grinder. Coffee grinders are used to grind coffee beans. The ground coffee beans are then brewed in water to create coffee. Thanks to the enormous popularity of drinking coffee, 50,000 coffee grinders are made annually. The image on the right shows the CAD model of the vintage coffee grinder that we wish to redesign using design for manufacturing principles. This particular coffee grinder works by rotating the crank on the right side of the grinder by hand. The burr grinder grinds the coffee beans, and the ground coffee beans get funneled into the drawer below for easy access by the consumer. This grinder works well for home use, but for food establishments that have to serve coffee made from freshly ground beans multiple times a day, this grinding process can be time consuming and inefficient. To speed up the process, we decided to replace the hand crank mechanism with a motor. These two versions of this vintage coffee grinder design can serve our two target customer groups: home coffee enthusiasts and small coffee shops and coffee serving food establishments. Our primary customers using the hand cranked grinder will be pleased with the unique vintage styling of the grinder, the ability to easily control portion sizes, and the personal customizability that comes with the hand crank mechanism. Our secondary customers using the motorized grinder will benefit from the addition of the motor because it allows the coffee shops and food establishments to produce coffee grounds faster to meet their larger coffee demand. Also, while the coffee beans are being ground, the worker responsible for making the coffee can step away and attend to a different task until the coffee beans have been fully ground. The primary difference between our two product varieties is the motorization of the grinding process for mass use applications.
Since last time, there have been some changes for new and altered parts for our assembly, including number 35, number 33, number 34 for the base and new drawer, as well as number 17, number 3 for the small gear, as well as number 9 for the helm, which will be explained later. For the functional analysis, the FAST diagram, the main purpose is to produce grounds, which includes containing beans, which is opening container, closing container, sealing the container, grind beans, which is provide motion, provide force, as well as dispense grounds, which is contain grounds and guide grounds, in addition to the normal please sense, enhanced product, assure dependability, which branches to support components, as well as assure convenience. From last time, nothing's really changed much with our functional component mapping matrix. Again, you can see that some parts only kind of have one purpose, whereas others may have many, such as the funnel. And then here is the second part of our functional component mapping matrix with all the other parts listed and their purposes. Here we have our FDT and CCT, which is the functional differentiation table and component commonality tables. This just kind of shows the what's different between customer groups, where similar to customer groups among the purposes, and this shows the parts that are pertinent to the platform or the part that's common between the two models, the automatic and the manual, and the modules are the parts that change with the manual versus the automatic. And speaking of, here are the two modules of the CAD. So this is the manual with the hand crank, and this is the module with the automatic with the automated motor.
Here's our product family design assembly sequences. As you can see, we have two options. The top option is what we're going with because it allows for delayed differentiation between our two different products, because we keep the production similar for the platform components and then separate off in the modular ones. Versus the bottom one, where we have two completely different manufacturing sequences, which would require duplicate machinery, increased costs, and reduced efficiency.
The assembly times of the coffee grounder are shown below. The case subassembly was chosen as the platform part because it took 41.56 seconds to put together. The main axle was chosen as the module part because it took 37.1 seconds to put together. Shown in the quad chart on the right, the main axle had a high functional importance but a low material and assembly cost. The case subassembly had a high functional importance and a high material and assembly cost. The assembly efficiencies before redesign was 22.68%, and the assembly efficiency after the redesigns was 32.62%. Shown below in the function component mapping matrix, the case subassembly is not exploded into multiple parts to save on space, but if it were, this would highlight the part consolidation that would happen here. The main axle is also highlighted because multiple functions are shared between the parts that will be consolidated in the module. The case subassembly before redesign is shown on the left. This was chosen because it had a high assembly time, but also high functionality. And the redesigns that we chose to do were DFIM1, which is to minimize the wall thickness, DFIM4, avoid sharp corners inside and out, and DFIM8 which was to integrate all 16 housing keys in place of ejection molding. The picture on the left shows in purple all of the housing keys that were integrated. In green, it shows the minimizing of the wall thickness. And in red, it shows the inside and out corners that are sharp that were in the redesign filleted. On the picture on the right, in the red, it shows all the fillets that were in it. In the green, it shows the minimized wall thickness. And there's no purple because all of the fasteners are now integrated in the design. So what did we do altogether? We reduced the part count from 22 parts to only 2. We changed the assembly time from 41.56 seconds to 11.3 seconds. We did not change the major functionality of the part, but we did reduce the manufacturing cost from 88 cents per part to 51 cents per part.
For the redesign of the module component, we selected to do the main axle. This is because the retaining rings and pins used to secure it have a very high assembly time of 37.1 seconds and don't contribute to the overall functionality of the product. In line with the core DFA principles of reducing part counts, reducing fasteners, and increasing part symmetry, we decided to thread the ends of the axles with an M10 times 1.5 millimeter thread at equal length so that it stays symmetrical. This updated design can be seen on the right along with its impact in the assembly. The original design can be seen on the left with colored callouts and their associated principles for design for assembly. So design for manufacturing, the math behind the component is the material cost comes out to about $1.13, coming from 1/2-inch bar stock at a length of 4 feet, which is easily available. The total cost of the component comes out to about $1.98, with the reduction of assembly time around 36 seconds. This is because some of the other times had to go up to account for the new mounting methods with the threads, with an estimated cost savings of around 20 cents per component.
As can be seen from our quad chart, the drawer subassembly is an ideal platform subassembly to be redesigned for automated assembly because we can see that it has high functional importance, but also a high material or assembly costs. It's also made of a lot of small parts that would work well in feeders. We can see that the main things it needs to do is to contain grounds, guide grounds, and assure convenience. So as long as those are still met, we're okay. So before redesign, we can see that the material cost is about 3 cents per subassembly. The total product cost, including assembly and handling time, is around 24 cents. And the total assembly time is 6 seconds because automatic feeders would make this have a goal of 10 subassemblies created per minute. So we can see that the principles that we want to use are DFA 1, 2, and 13, where we reduce the part count from 24 to 2. We reduce the fasteners from 19 to 1. And then we avoid adjustments because it turns into just 2 parts that doesn't need to be rotated a lot to put these pins in. So after redesign, we can see that this is a 2-part assembly, like I said before. We have the drawer, which is injection molded, and we have the same knob as before. So the material cost has actually increased from about 3 cents per subassembly to 10 cents per subassembly due to the injection molding. And the manufacturing cost for this is around 17 cents. So the total product cost is reduced from 27 cents to 23 cents with this redesign. And the total assembly time is unchanged because automatic feeders will still create 10 of these per minute. So it takes 6 seconds to make just one of these subassembly drawers.
Shown here is the process selection for our manual assembly platform, which is our base. And based on this analysis, we've chosen to use injection molding for this component. For our manual assembly module, we've decided to use the axle as this component, and we elected to utilize machining in order to produce it based on the analysis shown here. And in order to gain our tolerance and surface finish values needed to do that analysis, for the base, we chose to use an opaque high gloss surface finish as we want to be visually appealing to the customer, along with the tolerance of 0.25 millimeters, as we need proper mating between the funnel and base, along with a proper fit for the drawer. And for the axle, we chose to use a surface finish of 3 micrometers, as this will make it easier to clean old grounds off the surface, along with ensuring that it is visually appealing to the consumer, along with the tolerance of 0.1 millimeters, as we need to ensure consistent grind size along with proper mating between the axle and the mount cover half.
DfM Pro is a great tool for designers like ourselves. Looking at the platform component, the DfM Pro software found some issues with the sharp corners and the lack of a draft angle, which were easily resolved with the implementation of said draft angles and the softening of the edges. With regards to the module component, it had some issues with the threading with the sharp corners, but as many of us are aware, machining a thread is not particularly challenging, and as such, we felt it correct to override the DfM Pro's suggestions. Looking at the hubs quote, it predicted a total expense at $243 a piece for around 1,000, and then the exponential regression did not really work out for the 50,000 piece estimate. A realistic guess would probably be around $1.50 to $2, which is very close to the calculated cost that we found at $1.99.
In addition to our product, we plan on offering services to improve the customer experience, including offering repair services and providing customers with an instruction manual for how to operate our product. We also plan on reducing the negative environmental impact associated with the manufacture, distribution, use, and disposal of our product by replacing the wooden components in the design with injection molded plastic components made from recycled plastic. This will decrease the amount of deforestation and the amount of plastic in landfills. We made modifications to the 2 designs to make the manufacturing process and the assembly process more efficient and less expensive. This will help drive a lower retail cost for our product, which will allow a wider customer base to purchase our product. Further DfM analyses must be conducted on the other components of our product to determine whether there are potential savings elsewhere. If we were to change anything about the process, we would focus more on the function differentiation table and the component commonality table because the information from these tables set the stage for components that could be improved.